Well, I've been doing a little bit of pondering and a little bit of component finding to finally get all of the electronics and all the wiring tidied up on my Prusa copy. So I think I have come to some conclusions on how I'm going to do this, and I want to try and get the videos back to being a bit shorter, at least not always do long videos, because, well, I prefer little sort of bite-sized videos myself, so that's what I'm going to try and make. So what we're going to do is sort of break down, finishing off these electronics. There's a sort of few upgrades in there, there's a few, not really upgrades, but things that just needed finishing. So I'm going to sort of break those down into a few separate videos over this week, and so what we've got is Prusa Clone Electrical Upgrade Week. So what we're going to start with is the converting the heated bed to 24 volts. Now I'm not going to sort of claim that what I'm doing is the right way to do it. I'm obviously not going to claim it's the wrong way of doing it, because that would be a bit daft. But I'm not claiming it's the right way of doing it. There are in fact lots of different ways of doing this. And some people will go down the route of putting everything on the ramps at 24 volts. And there is some merit, I guess, into providing the stepper drivers with 24 volts. However, I'm not doing that. So the videos that I'm going to be doing, at least this first one, are going to be based around me wanting to just keep the heat bed at 24 volts. And also I want to keep the control of the heat bed separate from the ramps. Well, more or less. Obviously the ramps needs to tell it when to turn on and off, but I want to try and keep that 24 volts away from the ramps if possible. So there's a few things that we're going to need in order to do this. First of those really is a 24 power supply. A 24 volt power supply. Which I have. I've only got, I think it's 15 or 16 amps, which actually is going to be more than enough because I'm only powering the heat bed, and my calculations show that it will never get beyond 10 amps. In fact, it will never get near 10 amps. So 15 or 16 amp 24 volt power supply is amply good enough. Check, got that bit. The other thing that we're going to need to do is change the wiring on the heat bed. I have had a massive note written down to make sure you change the wiring on the heat bed before connecting it up to 24 volts, because as it's wired up at 12 volts it has about an ohm of resistance, which will give you a lot more current than I'm expecting. Yeah, so it needs to be wired for 24 volts. And the other thing I'm going to need is some way to control this outside of the ramps board, which is going to be the subject of this video. So like I said, there are plenty of different ways of doing this, and this may not even be the best way of doing it, but it is a way of doing it, and it will work, I hope. I'm mostly doing it this way because these are the parts that I have, and I just don't see any reason to go out and buy some more bits when I have perfectly usable bits here. So that is kind of dictating slightly how I'm doing it, but yeah, there are other ways. And I'm sure that any engineers watching this will, of course, rather do it a different way, but that's engineers for you. So without further ado, let's start by investigating, or going over my investigations and what I have concluded in terms of the components I'm going to use, most notably the Mosfet that I'm going to use, and yeah, get down to actually doing this stuff. And we'll start our little plan where all good plans start, and that's with the schematics. So this is the schematics for the Ramps 1.4 board that's freely available on the internet, and of course there will be a link with the rest of them. So basically what happens in your normal scenario is this is where your 4-pin connector is on the ramps board. So working in reverse order, this is the normal 12 volt earth, which we don't, well, earth ground, we don't really need to worry about that. This is your usual 12 volt supply that comes in, goes through the 5 amp polyfuse, goes off and does loads of other stuff, and in fact controls everything apart from the heat bed. So seeing as we're dealing with the heat bed, we'll ignore that. We also then have another ground for the other 12 volt supply, normally 12 volt V2, and here is that 12 volt V2, and that goes through this 11 amp polyfuse. Now the sole purpose of this V2 12 volt supply goes up and it comes in here. This is where this little section here is where all the heaters and fans and stuff are controlled, And basically we've got some inputs on this side, but more importantly we've got the 6 little screw terminals, the blue, well at least on mine it's blue screw terminals. They're on the ramps that you connect to the, well, heated bed obviously, the part cooling fan and the hot end. So we'll ignore the hot end and the part cooling fan because, well, we're not dealing with that. That's working fine. So it's these 2 connectors down at the bottom here that we're dealing with. So what happens is that second 12 volt supply normally comes in, like I said, from your power supply, and it goes effectively directly to pin 1 of that connector. What happens then is on the low side, i.e. the ground, that is switched via this Mosfet here, which is the one that causes all the problems because it's grossly under specified even for 12 volts, which is then driven by the D8 pin on the Arduino here. So what basically happens is your 12 volt V2 is permanently connected to the heat bed, and when Marlin decides it needs to turn the heat bed on to heat it up or turn it off to cool it down a bit, it triggers, it pulls D8 high, puts 5 volts into the D8 pin here, which comes along, goes through a couple of control resistors into this N-channel Mosfet, which then pulls this pin to ground through there, which is basically through here, and it completes the circuit and the heat bed gets hot. However, yeah, I'm going to be dealing with 24 volts, and you could in fact just do a little bit of jiggery pokery and actually run 24 volts through the existing ramps board, because like I said, this 12 volt V2 does nothing other than go straight out to this pin, so there's no real reason why you couldn't just change the MOSFET and a few other things. However, I want to keep my 24 volts completely off ramps, and there isn't really any room for a heatsink on the ramps board, so yeah, I'm basically going to run it all externally. So to make looking at this a little bit simpler, I have created my own schematic of what things will look like. And this is the same 4-pin input connector that we have on the ramps. This, in fact, this grey board here is a little piece of the ramps board. And these are the 6 pins that are going out. So we've got, I think, heated bed up here, fan and, sorry, the hot end here, the fan on these 2, and the heated bed here. Obviously, we're going to ignore those because we're not dealing with them. So what I'm going to do is I'm going to have my normal 12 volt supply coming in, and it's going to be split across both 12 volt and 12 volt V2, these 2 pins here going into the ramps. So both of them are going to have a 12 volt supply. The V2 ground is not going to have anything connected to it because it doesn't need it. Internally on the ramps board they are connected anyway, as you can see down here. The V1, if you like, and the V2 grounds are internally connected on the board. So I'm going to leave that one completely disconnected. I will then have my normal 12 volt power supply ground going into the ramps where it would normally go in, and yeah, so that's that. Then going to stick on a separate 24 volt power supply, and because we're going to need a common reference between these 2 parts of the power supplies, i.e. we need to join the ground of the 20 volt power supply to the ground of the 24 volt power supply to the ground of the 12 volt power supply. So we've got a common, effectively 0 volt reference there. So that, and the only reason I'm connecting V2 12 volt on the ramps is so that the LED still works. We don't actually need any of this. We're bypassing entirely all of this for our heated bed. However, rather than remove it, there's not much point in doing that, so I could just simply link the V2 12 volt supply to the V1 12 volt supply so that we can still power this LED when the heat bed is on. So again, we'll ignore the existing MOSFET on the ramps because we're not going to be using it. It's purely there now just to power the LED. And what we'll do is we'll tap into pin 8, the digital pin 8 of the Arduino. And from that we'll come off and we'll go through a current limiting resistor into a new MOSFET that's going to be, this is on a separate board, this bit over here. Yeah, so it's got a current limiting resistor just to protect the Arduino, and that's going to go into the gate of our new MOSFET. We'll also then just be making sure that when it's not active high, that it's being pulled down to ground by a 1 mega ohm resistor here, R2. Then what will happen is that the heated bed, the positive side of the heated bed, will be permanently connected to our 24 volt power supply, and the ground then will be switched via the MOSFET. So what that left me needing was a suitable MOSFET, and basically there are plenty of different ways of doing this. In fact, the whole scheme could have been done differently. Like I said, you could put a MOSFET on the board. You could also, if you wanted to keep it a bit cleaner, use the existing ground out, the switched ground out, which is there for the old style heat bed, the 12 volt heat bed. But then you would need a P-channel MOSFET, and essentially I didn't really want to buy any more MOSFETs because I've got loads of MOSFETs knocking about. So I had a look through the ones I've got, and this one from International Rectifier, I have an AUIRF B8409 in a TO220 package. Yeah, this will do the job nicely. One of the benefits of doing it this way with an N-channel, although it's a little bit more complicated, is that the N-channel MOSFETs tend to have a much lower resistance, RDS on, than the P-channels. So yeah, that's what we're concerned with here, because it's the RDS on which is going to sort of affect how hot it gets. So yeah, this is the datasheet for the MOSFET I'm going to use. I will also link this, of course, but to make life a little bit easier, I have taken out the relevant parts, if you like, and put them on a little slide here. So this is the MOSFET that I chose. Obviously it is well overrated for what we're doing. It can handle 40 volts and it can also potentially handle 195 amps. However, it is not really a logic level MOSFET, i.e. it really isn't. It's still in its ohmic region, I think, possibly up to around about 6 volts. Now we only have 5 volts and possibly a little bit less to play with. So I needed to do some fairly careful calculations, and those calculations are here on sort of roughly where it was in its ohmic region, around about 5 volts, and what kind of power that led to. I will not go through this now, but if you really want to read it all, you can just pause and have a look. The bottom line is that even with no heatsink, this MOSFET is going to hit 50 degrees C with a 25 degrees C ambient, so that's no problem whatsoever. I do have some heat sinks knocking about, so I'm going to slap one on, and that really is going to only increase about 9 degrees above ambient temperature, so it's going to run very cool. And obviously all of these I've painted with the most negative picture possible. It is very conservative, and it won't even reach that in all likelihood. So yeah, after I've decided that this MOSFET is, yeah, it should work, all in theory anyway, drawn up in circuit, no, not in circuit works actually, but anyway, a circuit simulation. So effectively what we have here is our 5 volts from the Arduino, the signal, and for, yeah, just to muck around with it, I've just put that on a switch. I have also added an LED here, and my 12k resistor, protection resistor, my 1 mega ohm pull down resistor, and a 150 ohm resistor just for limiting power to the LED. Here is our AUIR FB8409 MOSFET. Here is our 24 volt power supply, and here is our heated bed, which when used in the 24 volt configuration has a resistance of 3.6 ohms. So as we can see, we are currently off, and down here we can see that the heat bed is producing around about 0.21 picowatts. In other words, nothing, and that's good because there's no current going through it. So if when the Arduino goes high and this closes, obviously the LED comes on, it activates the gate of the Mosfet, so that connects the drain to the source, and current can flow through. And we can see we now have 159.27 watts being produced by the heat bed, and that is about 6.65 amps. So actually we're well below the 10 amps that I really gauged everything to, so there is no concerns here whatsoever. So everything's good. Yeah, we don't really need to say anything else there. I think it's now time to actually put it together. So I just grabbed a little piece of perf board. In fact, I would prefer to have just the perf board, but this one has the copper strips running down in lines. So it meant that I needed to sort of grind away some of the lines to make sure that the right bits were connected to the right bits and not the wrong bits. So yeah, a lot of twizzling, a lot of cleaning, and a lot of copper removal to make sure. So then I started putting on the 12k resistor and the 1 mega ohm resistor that we saw in the plan, and then a little bit of blue tack in order to secure it down whilst I soldered them all in place. Then I stick in my Mosfet and solder that down. In fact, I just solder one leg to hold it in place. And then what I'm going to do is, because obviously this is going to be passing a reasonable amount of current, in fact around about what, 6? Well, we'll call it 10 to be on the safe side. Obviously the copper traces can't handle that, so I'm using some 2.5 square mil copper wire just to beef that up. And yeah, so these are what's actually going to be carrying the current on the ground that this will be switching from the power supply to the heated bed. A little bit more cleaning up, and for good measure, because I got them hanging around, I'm going to stick a heatsink on. Probably not needed, but well, better safe than sorry. I then need to solder on the wire that's going to go to D8 on the Arduino, and just for good measure I decided to stick a LED on here. So there is the current limiting resistor being soldered in place to the gate side, i.e. the 5-volt side, and being grounded through the Mosfet, so that when the Mosfet kicks in, it will both have a 5-volt supply to the LED and a ground, and so should light up, all being well. So yeah, just solder the LED in, make sure that yeah, again, everything's connected to the right things, and that we don't have any what do you call them, bridges, and all good. Yeah, so there we have it. I have actually tested this, by the way, and it does work, and the the Mosfet literally gets, well, I had the heat bed up to 100 degrees C for like an hour or so, and the Mosfet only ever got to barely warmer than your finger. You could only just barely feel any heat in it whatsoever. In fact, the little red LED got warmer than the Mosfet did. So yeah, there's no issues there. Obviously there's some other bits to this story that I haven't covered yet, namely, well, there's only really one bit. There's the little yellow 24 gauge wire, I think it was, that I soldered on, that's going to control the gate on the Mosfet from the D8 pin of the Arduino. Obviously that needs to be connected to the Arduino, but I will be covering that when I do some little other changes to the Arduino and other changes to the ramps in the next coming videos. But other than that, yeah, that's everything, and it works. So, job done.